Okay, welcome to the second day of Anuj's lectures.
Okay, well, I should say thank you all for coming. I mean, it's always gratifying to see people coming back for the second lecture. Right, so in yesterday's lecture, I introduced a variety of logics, and I realized this in the class afterwards when you asked me to give you a summary, that there was a lot to take in. We're going to be talking mainly, I mean, a lot of it was building up to introducing fixed point logic with counting. This is the main focus of our study. And so it's a class of decision problems. I write FPC for a class of decision problems, right? I think of it as a complexity class. It's not really defined in terms of complexity, but it's a class of decision problems. The definition is those definable in fixed point logic with counting. Decision problems are always isomorphism closed classes of structures. I said finite relational structures, but you know, finite structures include things like graphs, Boolean formulas, systems of equations. These are the sorts of examples I will have of problems. Graphs most commonly. Every problem in FPC is in polynomial time, but the converse is false, and we will see this. Okay, there are polynomial time problems which are not in FPC. I gave an alternative characterization. So I gave a definition in terms of logic and alternative characterization in terms of relational machines. There's a natural machine class whose polynomial time restriction gives us exactly FPC. I'm not going to refer back to those machines again. I mean, that's more to show you the robustness of the definition, right? That this is capturing a natural notion of what I call symmetric computation. And I gave you a third definition, but not really, I didn't tell you why this gives us something similar, and this is what we're going to do. Well, one of the things we will do today is see why how symmetric circuits relate to fixed point with counting. So, we have a circuit. A circuit takes as input some relational structure. So, it has Boolean values for every relational atom over n. It has Boolean inputs, I should say. And it is symmetric if any permutation of n, the underlying universe, which I think of as just the numbers 1 through n, can be extended to an automorphism of the whole circuit. I think we elaborated this a little bit yesterday. Any symmetric circuit gives you an invariant Boolean function in the sense that the result doesn't depend upon the permutations, but the converse is false. There are invariant circuits which are not symmetric, and I gave you an example. I gave you a circuit for determining whether the number of edges in an n-vertex graph is even, which just used XOR gates, which was invariant because the property of having an even number of edges is clearly invariant under permuting the vertices, but the circuit wasn't symmetric. You can convert any invariant circuit to a symmetric one just by duplicating gates, but this can involve an exponential blow-up. Okay. Now, partly to motivate why we are interested in symmetric circuits, I'll give you, I mentioned there's an equivalence between polynomial size symmetric circuits or uniform polynomial size families of symmetric circuits in FPC. There's an easy direction of that, and that's the one from going from logic to circuits. I'll come back to the other direction later. But first of all, I'll give the easy direction because I think this gives us clear motivation of why we put this symmetry requirement on circuits. So let's start with first order logic. I give you a formula of first order logic. Let's say no free variables, it's a sentence. In the language of graphs, for example, so it's something that's true or false of any graph. And I want to construct a circuit, a family of circuits, for evaluating this formula. So I fix n, the size of the graph, the number of vertices. And now what do? I'm going to basically, take any subformula of phi. A subformula will have free variables, denoted by x bar. Imagine putting values in for those variables from among 1 through n, because 1 through n is the universe of my structure, so I can evaluate those variables, so I fix some assignment. So for each such pair of a subformula and an assignment of values to the variables, I create a gate in my circuit. So this is a gate, psi, A bar. Now what are the connections? Well, every formula has a connector at its head, what are the possibilities? If psi is theta 1 or theta 2, okay? So somewhere in my circuit I also have these gates, and I make this an OR gate. So the type of the gate is simply whatever the outermost connective in the formula is, that is fixed. And I do this. There's a subtlety here. Of course, not all the free variables of psi may appear in those formulas. So, you know, these tuples may be different. They may be shorter than A, but it's well defined. Okay. Similarly, for conjunction, negation, you do the obvious thing. The only interesting case is quantification. If psi is of the form there exists x theta, then what do? Well, this is just a big disjunction over n possible values of x, right? So you have theta a bar, let's just say a bar, extended with 1. Right? And this is psi a bar. Okay? You just take the big disjunction. It's nothing difficult here. Okay. So this is kind of an obvious translation of the first order formula into a circuit once I fix the size of the universe to be n. What can we say about this circuit? The depth of the circuit is a constant. It's given by the formula. Right? There's one, I mean, if you don't count what are called small gates, you know, fan and 2 gates, it's the quantifier rank of the formula, but otherwise it's the total nesting depth of the, well, it's the depth of phi, where depth of phi you understand the height of the syntax tree for phi. What's the size of the circuit? I say it's C times n to the k, where n is the size of the universe, C is the number of distinct subformulas, and k is the maximum number of free variables that appear in a subformula. Okay? Because for each subformula, I create this many copies at most. So that's the total number of gates. Okay? Note, I say maximum number of free variables in any subformula. When I restrict myself to formulas with a fixed number of variables, like in LK, that k serves as a bound of the maximum number of free variables in any subformula. That's exactly what it's there for. Okay? So we have constant depth, polynomial size, and the circuit is symmetric in the sense that now consider any permutation which applied to n, and I'll extend it to all the gates of the circuit by just mapping the gate psi a to the gate psi, apply pi to the values in a bar component-wise. And it's easy to see this is an automorphism of the circuit. It preserves all the connections, it preserves the labels of the gates, so it's an automorphism of the circuit. Okay? So from first order logic, we get a natural translation into symmetric circuits. This is the motivation for considering symmetric circuits. But why stop at first order logic? Consider fixed point logic. We now have we have these fixed point operators, but once we fix the size of the structure, we can unfold this fixed point into a first order thing, right? This is what I showed you before, last time, that you can iterate the fixed point at most some n to the k times, and you get a formula where the number of variables is still bounded by a constant k, it's just the quantifier depth grows to something like n to the k, right? So we translate the fixed point formula into a formula of first order logic using at most k variables for constant k. It's just the depth of the formula is given by some polynomial. Okay? C is, I suppose it's going to be, well, depends on the number of variables in phi, but k is an upper bound on both that and this. So this is going to be smaller than k. Okay. And this formula still has at most k free variables in every subformula, right? Because the total number of variables is at most k. It's as a formula of first order logic. Now this is a formula of first order logic. I apply the same translation. What do I get? I get a circuit. Now the size, the depth is no longer bounded by a constant in n, right? I have a different formula for each n, but it's bounded by a polynomial, and the size is also bounded by a polynomial. So I still get polynomial size symmetric families of circuits. or I should say polynomial-sized families of symmetric circuits. Okay. And I'm still using just ands, ors, and nots. Right? No other Boolean connectives, no other gates appear in my formula, in my circuit. What about if I add counting now? I have fixed point logic with counting. Sorry, that should be FPC there. Cut and paste error. Then there is a fixed k. Now I know that I can get, for any n, a formula in first order logic, but with counting quantifiers added, right? Quantifiers of the form that exists at least ix, such that something. But if I allow the counting quantifiers, I can still bound the number of variables by a constant. So I carry out the translation, right? It still has constant depth at most k-free variables in each subformula. I translate to the circuit. What happens? I still get exactly the same translation, except now I have to consider quantifiers of the form. There exists at least ix such that theta. So instead of a disjunction here, I have a threshold gate, right? Something which says that at least I of the inputs are 1. Okay? So I get a family, this is again FPC, of polynomial-sized symmetric circuits with threshold gates. Okay? Now, in the world of circuit complexity, threshold gates in the context of polynomial-sized circuits are not usually considered because you can just replace them, we know, with ordinary. You can compute a threshold gate with just ands, ors, and nots. But the point is we can't do this while preserving symmetry. You see, in circuit complexity for bounded depth circuits, for instance, there is a difference between what's called AC0 and TC0, and the difference is you add threshold gates. Okay? Here, also, if you restrict yourself to symmetric polynomial-sized circuits, even though depth is not bounded, adding threshold gates adds power. Okay. So this is why we're interested in symmetric gates. It turns out, instead of threshold gates, you could just use majority gates. So that's just one type of gate, along with and, or, not, and just majority. Turns out that's enough to do everything. Still symmetrically, you can simulate threshold gates. But I'm not going to worry about that. I'm happy to just take this basis. Okay. So the result, relating circuits and logic, are these two theorems. I kind of flashed them up at you last time, and I thought anyway. The second one basically says that the last translation I gave you has a converse. You can take any polynomial size family of symmetric circuits with threshold gates, right? And you can translate it to a formula of FPC. If it's a uniform family, polynomially uniform, polynomial size, families with circuit gate, it can be translated back to FPC. So this is an equivalent characterization of FPC. And I'll give you, and so we've seen one direction of this, pretty much the easy direction, and I'll give you in the latter part of this lecture an indication of how you prove the converse. If you don't put threshold gates and you just use and, ors, and nots, it's a little bit more subtle. You don't exactly get FP, right? It's not a converse to this for the kind of silly reason, which is this. Consider the following family of circuits is just trivial circuit, output 1 if n is even, output 0 if n is odd. Right? It does nothing on the gates. It just tells you whether the number n is odd or even. They're obviously symmetric. There's nothing to consider here. But we saw that in fixed point logic alone, you can't do this. You can't tell whether this number of elements is odd or even. Okay? So for this entirely silly reason, you can't translate symmetric Boolean circuits to fixed point logic. You have to enhance the power of fixed point logic to basically just be able to at least, because the circuit restricted, they're uniform circuits, which means any computation which depends purely on the size of the circuit and can be done in polynomial time should be doable. So what we do is we consider inputs. We interpret fixed point logics not just on a graph G, but on the disjoint union of a graph with a linear order whose size is exactly the size of the graph. Okay? This is a structure. And now we talk about the expressive power of fixed point logic on such things. I mentioned this in the class yesterday. I showed you in the lecture that you can't do existence of perfect matchings in fixed point logic. And then I showed you that adding this linear order, which just tells you the size of the graph G, you still can't do it. Well, this exactly characterizes symmetric Boolean circuits with AND or NOT gates. Okay. So again, so that's the connection with circuits. But before I get to, as I said, I will get to showing you how you translate circuits to formulas, or at least give you an idea of where the work is in the proof. But before that, I want to go on and talk a little bit about the expressive power of FPC, right? We've now got three different characterizations: circuit, machine, and logic. What do we know about its expressive power? Well, FPC is quite powerful in the sense that, so when Neil Immerman first suggested this logic, he said anything that's obviously polynomial time, you can usually write it as an FPC formula. What does obviously polynomial time mean? Well, the most kind of algorithms you think of translate into FPC. And the first example of something that's polynomial time but not FPC was certainly not obvious, right? It's a rather difficult example, and I'll look at it in a moment. So, in particular, it includes P-complete problems. So the circuit value problem, classic P-complete problem. I give you a circuit. We know what a circuit is. Let's say AND or and NOT. Let's say the inputs are all labeled with zeros and ones. Decide the value of the output gate. So the input is now this structure. Evaluating it, this you can do in fixed point logic. You don't need counting, right? You just inductively, on the structure of the circuit, determine the value of every gate. If I add threshold gates here, I need to be able to count, right? But it's clear that circuit value problem with threshold gates is still FPC. Okay, it's kind of, I mentioned this because in the translation from circuits to FPC, this is a valuable, this is an essential element. But, so this is a P-complete problem, okay? So in ordinary complexity terms, it's as hard as you can get in P, but that's in this logic. But you can do much more. There are many non-obvious polynomial time algorithms that turn out to be in FPC, and I should mention here, GROW is monumental work, which shows that any polynomial time property over any proper minor closed class of graphs is in FPC. This reproduces this whole Robertson-Seymour theory of graph minors inside FPC. So this is far from what I would call obviously polynomial time. And part of what I'm going to do tomorrow is show you that, so in FPC, we can express the existence of perfect matchings in graphs. This was an open question for many years. And we do this by showing that you can essentially do linear programming techniques inside FPC. Now, it's kind of, the way I think of it is, matching was shown to be in polynomial time by Edmonds in the 1960s. Linear programming was shown to be in polynomial time by Kacyan in late 70s, 1980. This whole graph minor stuff was shown to be polynomial time by Robertson and Seymour in the 90s. Each of these was a major achievement to show that it is polynomial time. So that's why I mean by they're highly non-trivial polynomial time algorithms. Each of these was a significant result in itself. But they turned out to be all in FPC. And yet the problem that is, we know that there are things that cannot be expressed. Cypher and Immerman constructed the first example in terms of graphs. But it turns out that there are, in some sense, simple XOR SAT, right? Determining the satisfiability of a collection of clauses with just XOR. Or slightly more generally, solving a system of linear equations over a finite field. Yes?
We know about checking primalities in FPC?
In some sense, so To check primality, the input is a number. A number is a naturally ordered thing. It has no symmetries. And on ordered structures, everything in polynomial time is FPC. So in principle, you can translate that. In some sense, that's an uninteresting case. It's for where inputs have symmetries that this becomes an interesting issue. So solving systems of linear equations over a finite field is not an FPC. And this is kind of, think of it this way. Highly non-trivial algorithms can be translated to FPC. The linear programming ellipsoid method turns out, these Robertson-Seymour graph minor things. But it turns out Gaussian elimination you cannot do. It's a simple polynomial time algorithm, but it cannot be symmetrized. And just think about this for a moment. What is Gaussian elimination? You have a matrix, you choose a pivot, you do this. You essentially subtract two rows or whatever. You perform elementary row operations. This choice of a row on which to do it is arbitrary. But we know, essentially because of the structure over which you're working, that the choice doesn't matter. The result will be the same. Okay? You try to symmetrize this and try to do all choices simultaneously, and it blows up exponentially. And this really says there's no way around that. Okay? That's what this result is telling us. Okay. So then there are NP-complete problems which we can prove are not in FPC, okay? Including satisfiability, Hamiltonian cycle, three-colorability. Okay, I'll give you some indication of why this is the case. There are other NP-complete problems for which it's unknown, okay? And there are NP-complete problems for which the question of whether they're an FPC is equivalent to whether P is equal to NP. I mean, in particular, you could always take an ordered, a problem on numbers, for example. So that's maybe not that interesting, but there are more interesting ones as well for which this is the case. Okay. So here, so how do we prove that something is not an FPC like this? Well, we rely on this translation that I've told you. That is that any formula in FPC is invariant under the CK equivalence for some constant K, right? Because you can translate the formula for a fixed size of structure into a formula of CK. If two things cannot be distinguished by any formula of CK, they cannot be distinguished by phi. Okay? So, okay. That's what we want to do, and now we're going to go to constructing pairs of structures which are CK equivalent for arbitrary K. But how do we show CK equivalence? So the first thing is, an Ehrenfeucht-Freisey style game. Okay, so I talked last time about this K-pebble game, which gives us equivalence for LK. You have K pebbles on the board, A and B. At each move, spoiler picks a pebble and moves it to another element, and duplicator has to respond on the other structure. Okay? The K pebbles correspond to the K variables. You can simultaneously refer to elements of the structure, and the moves correspond to quantification, and there's essentially unbounded number of moves. So what do we have to do to change this game to CK? So the first, the Immermann and Lander defined this game, where again we have spoiler and duplicator with K pairs of pebbles. Now at each move, spoiler picks a pebble number I, and a set of vertices in one of the structures. Okay? Duplicator has to respond with a set of vertices in the other structure of the same size. Spoiler places pebble AI on an element. Well, I mean, if duplicator chose a subset of A, then spoiler places an element AI on an element of Y. If spoiler here had chosen a subset of A and duplicator had chosen a subset of B, spoiler would be placing BI on an element of the set chosen by duplicator. Maybe that's a bit complicated, but maybe the easiest way to understand this is we want to think of a game where there exists at least I well, let's not use I because I is there, sort of T. There exists at least Tx such that theta is, let's say, true in the structure A and false in the structure B, right? And Spoiler wants to demonstrate this. Spoiler knows this formula. How would Spoiler do this? Well, choose the set of elements for which theta is true in A. Duplicator has to respond with the same number of elements in B. But if this formula is true in B, then for at least one of those elements, theta must be false, right? So Spoiler places a pebble on that element. Duplicator places a pebble on the element in the set that Spoiler had chosen here, but by definition, I mean by choice rather, theta is true for all of these. So now in the remaining pebble position, theta differentiates them. And this is an argument by induction on the quantifier rank. Spoiler has a winning strategy to win, okay? So at any stage, this is the usual thing. Spoiler wins if the map is not a partial isomorphism. And so if Duplicator has a winning strategy to survive for P moves, then there's no formula of quantifier rank P that distinguishes it. Okay, because if there was such a formula, it would give a winning strategy for Spoiler. Okay, so I did it with an existential, with a, you know, obviously with a negation, you would play in the other structure. Okay. So this was defined by Immerman and Landa. Curious, does everybody know who Neil Immerman is? No, I guess most people don't. All right. I was then going to say, do you know who Eric Lander is? But I bet you don't know who Eric Lander is. You do know. Okay. Immerman, of course, is well known in the sort of logic and computer science field, but Eric Lander is not a computer scientist at all. And I only knew him through this paper, and I always assumed he was somebody who left research until I read about him in the newspapers. But a few years ago, when he was chief scientific advisor to Barack Obama, not on the strength of this work, I should say. But anyway, okay, so this is actually the version of the game that Cypher and Immerman originally used, but it's rather easier to describe the construction in terms of an alternative game due to Lauri-Hella, which is the k-pebble bijection game. This works as follows. So we have a pair of structures. Again, we have k-pebbles, A1 to AK on A, B1 through BK on B, and that's a position in the game. At each move, Spoiler chooses a pair of pebbles that are going to move, and Duplicator has to give a bijection between the universe of A and the universe of B, which for those pebbles which are not moving, you know, maps the current pebble position. So it preserves the current pebble position, but it can do, you know, change everywhere else. Okay, and then Spoiler chooses an element of A, and AI goes on that element, and BI goes on its image under this bijection. So think of this. This is like the ordinary k-pebble bijection game. K-pebble game I defined for LK, where Spoiler moves an element and Duplicator has to respond, except Duplicator in some sense has to in advance give all possible responses to Spoiler's moves, and these have to form a bijection between A and B, right? These all possible responses, okay? And the same winning condition, if we reach a point where this is not a partial isomorphism, Duplicator has lost, and otherwise if Duplicator, again I could have said, Duplicator has a strategy to play for P moves, then they're equivalent for up to quantifier rank P. Equivalently, if Duplicator can play forever, then they cannot be distinguished. So I convinced you that the Immerman and Lander game characterizes this counting logic. So maybe let me convince you that the bijection game is equivalent to the Immerman-Lander game, right? And then it'll be clear. So why is this the same? It's equivalent in the sense winning strategy for Duplicator in one works in the other. So one direction is easy. If Duplicator has a winning strategy in the bijection game, then you get a winning strategy in the Immerman-Lander counting game, because whenever Spoiler picks a set in A, you respond with its image under the bijection. and spoiler picks a set in B, you respond with its pre-image under the bijection. That gives you a set of the same size, and clearly that wins the counting game, because spoiler now places a pebble on an element of this and an element of this. Spoiler places a pebble on an element of this, and you respond with an element inside that by taking just its image under the bijection. So clearly, bijection game is harder for duplicator, or at least as hard. In the other direction, suppose I tell you that duplicator has a winning strategy in the counting game. How do you get a winning strategy in the bijection game? What you do is the following. Consider the current position in the structure A, right? So A is currently pebbled positions. We know that pebble number I is moving. Look at all the places it could move to, right? And say that two of them, A and A prime, are equivalent if they're not distinguished by any CK formula. This is an equivalence relation on the elements of A. Okay? It partitions A into sets. For each of the parts, imagine spoiler playing that part, and we know duplicator has a response on the other side. Okay? And this response is a set of the same size, and it's easy to show these things can't overlap in B. So take the corresponding parts, there are bijections between them, put it all together, you get a bijection between all of A and all of B, and you can show this must be now a winning move in the bijection game, because whatever element spoiler now moves the pebble to, it turns out the one on the opposite side still satisfies the same CK formulas, right? So you can translate a winning strategy in this game to a winning strategy in the bijection game. Okay, so bijection games are easier to argue with, that's why we take them. And now I'm going to move to the Seyfert-Immermann construction, which first gave us a polynomial time graph property that is not in FPC. And what they do is basically they construct for each k a pair of graphs which are CK equivalent, and this we will prove by means of a bijection game. But there is some polynomial time class of graphs which includes all GK and excludes all the HK, and therefore this polynomial time class of graphs is not closed under this equivalence relation for any k, and therefore not definable in FPC. Okay. So in particular, this also showed that there is no k for which this is exactly the isomorphism relation between graphs. Okay. At the time when Seyfert-Immermann proved this was also an open question in terms of what are called the Weisfeiler-Lehmann equivalences. So these are the two kind of main consequences of their construction. Okay. So what is the construction? So we start with some graph G. Okay. And then we're going to define from this G two graphs. Well, first of all, I'll define one graph xg, and then the other one will be a slight variation of xg. And it is obtained by replacing every edge in G with a pair of edges and every vertex with a gadget. Well, I'll just show you the gadget, but maybe expand over here what the properties are, okay? So we have a graph G, and imagine this is a vertex in G, okay, of degree 3. It's going to be replaced with a gadget. It's going to be replaced with a gadget like this, okay? If the degree is bigger, the gadgets will be bigger as well. So what is the gadget? This edge is going to be replaced with a pair of edges. Each edge is replaced with a pair of edges, right? And so these are part of the vertex gadget, and there are going to be 4 in the middle. I say 4. This is because it's degree 3. In general, for degree d, there will be 2 raised to the power of d minus 1. So if it was 4, there would be 8. If there was 5, there would be 16 in the middle over here. Okay, why? There is one vertex in the middle for every even size subset of the 3 edges. Right, so I'm calling the 3 edges the three neighbors of V in the original graph, call these W, this is V, this is W1, this is W2, and this is W3, right? And so each edge has been replaced with these two, and so I call this A W1 and B W1, and there's an A W2 and a B W2, etc., and a B W3. Okay? For each even-sized subset of 1, 2, 3, I have a vertex in the middle, and each of these is connected to one of these, and one of these, and which ones it's connected to is given by the subset. So if it's empty, the empty set, I connect to all three B's. I have the set 1, 2, so I connect to A1 and A2, but to B3. When it's 1, 3, I connect to A1 and A3 and B2, and this one I connect to A2 and A3 and B1. Okay? So the main property of this, easily verified, is if I just consider this gadget, if I swap A and B, I can extend this to an automorphism of the gadget, but I have to swap exactly one of the other two. Right? That's why, because these are even-sized subsets. So I can swap A and B for any even-sized subset of W1, W2, and W3 and keep this gadget looking exactly the same. Right? So up to automorphism, we can't really tell the A's and B's apart, except kind of collectively. We can't swap all three. We can't swap just one, but we can swap any pair, any two of them. That's the key property of the gadget. Okay, so now I've pretty much told you what the graph XG is. I started with the graph G and I replaced everything with a gadget like this. And now I get a different graph X tilde G, where I construct it exactly like XG, but in one particular vertex, instead of the even-sized subsets, I take the odd-sized subsets. Right? So subsets of size 1 or 3. It's the other 4. Okay? I get something which is different. It's X tilde G. And it's not isomorphic. Because of the property I just showed you, you can show that these things are not isomorphic. And now we want to show that they're hard to distinguish. Okay. So as long as the graph I start with, this original G, is connected and has tree width at least k. Does everyone know what tree width is? I have a definition in a couple of slides, but I just, no? Okay, I'll come to that in a moment. It's basically a measure of connectedness of the graph. High tree width means it's a highly connected graph. Okay, it turns out that if G is connected, then these things are not isomorphic. And if the tree width is at least k, of the original graph is at least k, then these things cannot be distinguished in CK. Okay, so this gives us the family of graphs we were looking for. And constructing a polynomial time property separating XG and X tilde G, I'm not going to go into the details. You know, that we can get a polynomial time property. I'm more interested in the second. How do we prove this? And we're going to use a bijection game to prove it. Okay. Now, so tree width. Roughly speaking, the tree width of a graph is a measure of how tree-like the graph is. This is a very, very rough measure. Okay. Basically, if you can cover the graph using small size patches, size at most k plus 1, then in a tree-like fashion, right, then it has small tree width. That's the intuition. I have a formal definition. I don't know if this is going to be much use if you haven't seen it before. Keep the intuitive picture in mind. Formally, for a graph, we have a tree decomposition. And that's a tree together with something which relates to every node of the tree, some subset of the vertices. For every vertex, the collection of nodes in the tree to which it's related forms a connected subtree, and every edge is covered. For every edge, both endpoints are related to some node. Okay, that's the formal definition of a tree decomposition. And the tree width is just the smallest k, such that we can get a tree decomposition where every bag has size at most k plus 1, bag being defined as the set of vertices of the graph related to any fixed node in the tree. Okay? I'm not going to use this formal definition. What I'm going to use is this nice characterization by Robertson and Seymour in terms of Cops and Robbers games. Okay? So this is the following game. You have an undirected graph G. We have two players. One of them is in charge of a team of k cops, and the other one is in charge of a robber. At any point, the cops are sitting on some set of nodes in the graph, some set of vertices, at most k, right? Because there are k of the k cops. And the robber is sitting on a node R. What's one move of the game? The cops are trying to catch the robber. In one move, the cop player removes some cops and announces where they're going. Right? Basically, these cops have helicopters. They get in there, but they're rather noisy helicopters, so you know where they're going to land. They can go anywhere in the graph. They're not restricted by the graph structure at all. Okay? But the robber is restricted to moving along edges of the graph, but super fast. You can, not just one edge, you can go along any path. So the robber can go along any path from the current position to a new point, as long as it avoids the cops which are not in the air. So you can't go through any node where the cops are stationary. Okay, that's the game. We end up with a new position, which is the cops that didn't move and the places where they landed, and the robber in node S. If the robber is in the same place as a cop, the game is over and the robber has lost, otherwise it can carry on. Okay? And this is the theorem of Robertson and Seymour I want to use. Is there's a winning strategy for the cop player with k cops if and only if the tree width of G is at most k minus 1. Is at most k minus 1. That's right. So kind of one direction is easy. From a tree decomposition, you can derive a winning strategy for the cops. You land the cops on the root of the tree, on the vertices, there are at most k of them. Robber is forced into one of the branches, and then now you move the cops to the bag at the root of the next of the subtree in which the robber is, and robber can't get out of that subtree, and you carry on in this fashion, and you'll get to the bottom of the tree decomposition, and robber will be caught. The other direction is more difficult, but we don't need to worry about it. All I want to do is the following. I'm going to say, okay, what I'm going to want to do is, I have this graph G from which I formed xg and x tilde g, right? From G, I formed xg and x tilde g. And now I said if the tree width of G is large enough, then these things are CK equivalent. And how I prove that is I take this cops and robber winning strategy, the winning strategy for robber on G, and turning it into a winning strategy for duplicator in this bijection game. Okay, that's what I want to do. For our purposes, okay, if you don't want to worry about tree width, to make the result I want, all you need is that there is a graph on which a robber has a winning strategy, again, for any k, right? That's all I really need. For every k, I can give you a graph, and I'll give you a concrete such graph. We want to call the k by k toroidal grid. This is this graph. K vertices this way. K vertices this way in a grid pattern. But why toroidal? Well, I'm going to make this a regular graph by also wrapping it around in both directions, right? Okay, so think of it as embedded on a torus. That's why I call it toroidal grid. Okay. And now let me at least convince you that on this graph, if this is k and this is k, then robber has a winning strategy against k cops. Okay, So why is this? Well, the point is that if you choose any k vertices on this, any k vertices, and remove them, right? In some sense, they're occupied by cops. We can't use them. The rest of the graph still contains more than half the total vertices. Sorry, no. That's kind of obvious. The rest of the graph contains a connected component with more than half the total vertices. Okay, why is this? Well, suppose X is my set of k vertices. If X only contains vertices in distinct rows, then removing X doesn't even disconnect the graph, right? Because in each row, I can still go all the way around, right? So the rest of the graph is still connected. So it's large. Okay. So suppose that X doesn't contain vertices in k distinct rows. That means for some row, there's no element of X at all, right? Now I claim this row, I have one row which is free of X. Look at the columns. If a column contains 0 or 1 elements of X, everything else in it is still connected to this row, right? So how many columns contain two or more elements of X? Well, it's at most k over 2, right? So there's at most k over 2 columns which have anything disconnected from this row, right? So for at least k over 2 columns, everything on the column is connected to this row, and that gives me a connected component with more than half the graph. Okay? So there we go. Now, what is the robber's strategy against k-cops? The strategy is simply stay in the large component. Robber is at any point, at some point in this grid, right? And this is the large component in the sense that it's connected to more than half the graph while avoiding X. Robbers move from X to some other position. Well, we know whatever the new position is, there will be a large component. These two large components are both more than half the graph, so they have a non-empty intersection. Robber just moves to somewhere in that intersection. That guarantees that at the next move, robber is still in the large component. And do this forever. Okay? So there's no, yeah. Okay. So we have a graph where robber has a winning strategy. How does this translate into a bijection game between xg and x tilde g? So, remember what xg is. We've taken this g and replaced it with these gadgets, and x tilde g we have the same, sorry, except basically one way of thinking of it is in one of these, for one of these pairs, for one particular vertex, we interchange these two, right? And this is only at one vertex in x tilde g. So now, Duplicator is playing bijections. Duplicator will always play a bijection which everywhere except one vertex, if you remove the gadget for one vertex, the rest of it is going to be an isomorphism on the rest of xg. First move, it'll be obviously a bijection everywhere except where this is bad. Okay? Now, in some sense, every time spoiler moves in the bijection game, Duplicator is going to change the bijection to hide this inconsistency somewhere else in the graph. And this hiding is exactly the cops and robbers game on the original graph G. There's one node in the original graph G where the inconsistency is. You're hiding it. And the k current pebbles in the bijection game, you think of as a cop position on that original graph. Okay? So a bijection is good except at a vertex V if it's an isomorphism everywhere except this, the vertices corresponding to V. And now the point is that if there is a path from V to U in the original graph G, then you can, for any bijection, you can come up with a new bijection which is good everywhere except at U now, instead of V, and you change the bijection only along the path from V to U. That's the key. And why is that possible? Well, that's the property of these gadgets. To change this, I want to make this one good, I have to swap these two in my bijection, right? This was previously going to this and this to this. If I change the bijection, this becomes consistent over here. But in order to change that, I have to change the other endpoint of this edge, which changes at another gadget. And I have to change the next one. And essentially, I have to follow along a path, because at any gadget, I can change any two, but not all three, or not just one. So I can move this as it were, this inconsistency anywhere along a path and move it somewhere else to get a bijection which is good everywhere except at U. Okay? And so, whenever Duplicator plays the bijections that are good bar V, where V is the robber position in G, and whenever, so spoiler moves a pebble, you hide this inconsistency somewhere where away from the K current pebbles by following the robber winning strategy in G. I hope the idea is clear enough. Okay.
Actually, why these two graphs are not isomorphic?
Why are the two graphs not isomorphic? Well, if you just essentially map, how do
the gadgets alone are isomorphic, but the entire graphs are not.
That's right. I mean, the point is that to map this gadget to this gadget, right? You have to essentially map AB to BA over here for one particular edge. And then to extend that to the other endpoint of this edge, you have to swap them around as well. Okay? You have this two, I mean, I don't know how to, I can kind of prove this. Maybe
I think, well, you can define some invariant which will, basing on how you define the bijection, which will be some numeric invariant, which turns out to be 0 in one case and 1 in the other case.
Exactly, and that's, I was trying to give some intuition rather than going through this kind of formal argument, but I'm not, so, roughly speaking, the way the formal argument works is, you know, you have it turns out that for each edge here, you have two possibilities for this. You know, you look at the automorphisms of the whole graph XG, and they correspond to a subspace of Z2 to the E, right? Basically, you can. But because of these gadgets, it's not the whole space, all right? This kind of enforces you get a subspace of half the size, and from this you can then show that the orbit under isomorphisms of this graph is exactly half of the possibilities, and this falls in the other half. I mean, there's a formal argument along these lines, which is what Cypher and Immerman give, but it's
so trivial.
It's not so trivial, yes. Okay. So we have our first example of something that's not in FPC, and this kind of motivates the following definition. You have a class of structures. I define what I call its counting width, which is a function, where mu C of n is the smallest value k, so that when you restrict C to structures with at most n elements, it's closed under this CK equivalence relation. Okay, so nu C of n is at most n, because we know that this is an isomorphism closed class of structures, and we know that n equivalence is isomorphism on n-element structures, right? If you let k be as big as n, then it's isomorphism. So this is at most n, but it in some sense is a measure of how close the class is to being invariant under CK. So anything definable in FPC has counting width bounded by a constant. That's just the statement we made earlier, that anything definable in FPC is invariant under CK equivalence for some fixed value of k. The Cipher-Immelmann construction that I just showed you shows a class of graphs whose counting width is bounded below by something order of square root of n. Why square root of n? Well, my grids have size k squared. They're 4 regular, so when I replace the nodes in the grid by the gadget, I'm expanding it by some fixed constant size, right? I'm replacing every vertex here by 16 vertices, okay? So my xg and my x tilde g have size 16 times k squared, so hence the square root of n, right? The number, the k is square root of the size of the graph, order of the square root of the size of the graph. We can do better. Turns out you can get a linear lower bound, and this was already in the original paper by Cipher-Immelmann. Instead of grids, you consider expander graphs. You can get, you can start with a graph of some constant times k number of vertices, which is sufficiently connected to make this argument go through. Okay, so we can get linear lower bounds. Now, we have one problem for which we have linear lower bounds on counting width. We can transfer this to other problems by notions of reductions. So what kind of reductions do we want to allow? Right? It's not polynomial time reductions. We know that FPC is not closed under such reductions, because I gave you a P-complete problem which is in FPC, but FPC is not all of P. And so even AC0 reductions, weak reductions are not enough. We want sort of reductions which preserve symmetries. So we look at reductions definable in logic. There's a standard notion of interpretation. So roughly speaking, well, more precisely speaking even, we have 2 relational signatures, sigma and tau. And a first order interpretation of tau and sigma is a tuple of formulas. I didn't want to use k here. I think I changed the k to d over here, but pretend that k says d, okay? We have a collection of first order formulas that says that for some d, the free variables of pi u are among x1 through xd, and the free variables of pi I, right? So there's one formula for each relation symbol in tau. Each of these formulas is in the vocabulary sigma, and pi I has free variables among x1 to xd times ni, right? So this is d, and ni is the arity of ri. And we call d the dimension of the interpretation. What is this supposed to mean? Right? This is just a sort of piece of syntax. It's a collection of formulas. The idea is that an interpretation of tau and sigma takes sigma structures to tau structures. It's a way of defining a function using formulas rather than just defining classes of structures. So you start with a sigma structure, and we get a tau structure whose universe is those d tuples in A which satisfy this one, the first formula. And for each relation, the relation Ri is interpreted by in B by the tuple satisfying pi I, right? These are now, okay. More generally, we can also consider interpretations which not just define the universe, but take its quotient under some definable equivalence relation or congruence relation. I'm not really going to be that much concerned with the details, but what I want to say is this gives us a notion of reduction. So a class of structures, C, is reducible to a class D if there is a first order interpretation such that for any structure A and C, its image under this is in D, if and only if, right? So, I mean, the usual notion of a function being a reduction, we've just defined what it means to define a function from sigma structures to tau structures in first order logic. Okay, so we say C is first order reducible to D. One class is first order reducible to another. We can do this more generally for any logic. We can do it for FPC. And the key observation I want to make is, if you can reduce one class to another, let's say in FPC, so in particular also in first order logic, then the counting width, as I defined it, of D is bounded below by the counting width of C, right? This is what you would expect. So reduction from C to D shows that D is at least as hard as C. And why do I get this counting width raised to the power 1 over D? Where's the loss coming from? It's not really an increase in the number of variables. So why is this true, first of all? Well, the point is that if D is invariant under CK equivalence for small k, you can then translate that, the CK definition into something which defines it on C. You need to multiply the number of variables by D, but that's not accounting for this factor. This factor comes from the change in the size of the structure. With a D-dimensional interpretation, you might be going from a structure in size n to a structure of size n to the D. Okay? And so the lower bounds here is in terms of structures of size n to the D, so it gives you lower bounds here on structures of size, the size raised to the power 1 over D. Okay, so if you can make sure the reduction maps things to structure instances of linear size, then you can actually literally lower bound nu D by nu C. Okay? And it turns out, I've mentioned various problems for which we know they're not in FPC. In fact, we can show from pretty much all of these that they have linear lower bounds on their counting width. And essentially, this is by defining suitable reductions from the CFI construction that we started with, right? Once we have one, by means of reductions, we can show lower bounds on lots of others. And I might pick this up. Let's see. In the class after this lecture, we'll look at this in a bit more detail. Okay. So this has taken me a little bit longer than I thought, but that always happens. I want to get back to talking a little bit about circuits. So I flashed this equivalence, and I promised you that I would give you the harder direction, or at least some indication of how the harder direction of this theorem is proved, the equivalence between. Now we know a little bit more about FPC. We know we have inexpressibility results, and the point is, I want to show that those really give you real circuit lower bounds, and for that I want to show this equivalence of circuits in FPC. So how do we go about this? Okay, so I just have some consequences I wrote of the result. Maybe I'll skip this bit. Okay, this is, you can read it, but in some sense I'm not going to go further into this. Let's see how we go about proving our result. Maybe I can skip over this bit too. Okay. Let's go on about. Okay. So now I want to show you how I can translate polynomial size symmetric circuits into FPC. Obviously assuming they're uniform circuits, so that we're still computing properties in polynomial time. Now our symmetric circuit has the property that the action of Sn extends to an automorphism of the circuit. In fact, I'm going to make a stronger assumption that these are all and only the automorphisms of the circuit. In other words, all of these are in fact non-trivial automorphisms of the circuit, and there are no others. Why can I assume this? Well, first of all, so first assumption is that every permutation in Sn gives rise to a non-trivial automorphism. If it doesn't, then there is some, let's say, input some permutation which doesn't move anything, and let's say that permutation swaps, let's say x, or moves x to y. Now if this doesn't move anything in the circuit, then x cannot appear in any input to the circuit, right? Because if it does, it has to move. So in other words, if you have somewhere in the circuit the input x, z, then under the action of this has to move somewhere else. So if this permutation doesn't move anything in the circuit, x cannot appear anywhere in the circuit. But then by symmetry, no input can appear in the circuit, and so the circuit is just computing some constant function. Okay? So it's fair enough to assume that every permutation gives rise to a non-trivial automorphism. And the other is that there are no non-trivial automorphisms which fix all the inputs, right? Because if there are, then really what that is saying is you have a bunch of inputs and you have further gates, maybe, and you have redundant gates because you can swap them around without changing any of the inputs. Okay? And if you have, then you can eliminate them. We can show this, in fact you can do this inductively, eliminate all the redundant gates, and then you end up with a circuit whose automorphisms are exactly those generated by permutations of Sn. So in other words, the automorphism of group of the circuit is really isomorphic to Sn as a group. Okay? We make this assumption. We call such circuits rigid. Okay. Now, at any gate in Cn, we define the stabilizer of G as just those permutations for which don't move this particular gate. For example, if you have an input corresponding to, as I said, 13, 17, right? This is going to be when the graph is input 1 if there's an edge between these two nodes and 0 if there isn't. Then a permutation which only moves 1 and 3 and nothing else doesn't change this gate. But a permutation that moves 13 will move this gate somewhere else. Okay? So for every gate, I mentioned it for input gates, but for every gate, there's some subgroup of Sn, which is those permutations which fix the gate. We call that the stabilizer. The orbit of the gate is those gates to which G can move under the action of some permutation. And standard sort of fact from permutation group theory is that because this is exactly the automorphism group, there is exactly one gate in the orbit for each coset of the stabilizer in Sn, right? So you can identify the gates in the orbit of G with the cosets of this subgroup of Sn. So in particular, we can say how big the orbit is. It is simply Sn, the index of the stabilizer in Sn, in other words, n factorial divided by the size of the stabilizer group. So if we are talking about polynomial sized circuits, therefore the orbit of every gate is bounded by some polynomial, this means that the stabilizer of every gate is pretty big, because this is at most polynomial in n. Okay? So an upper bound on the stabilizer gives a lower bound on the orbit. So if the stabilizer is small, the orbit is big, and the circuit must be big. Okay. Conversely, if we know the circuit is polynomial size, the orbits are of polynomial size, so the stabilizer is big. Note again this special case. What's the stabilizer of this? It's all permutations that fix these two particular values. So there's n minus 2 factorial of them. And so the stabilizer is n minus 2 factorial, n factorial divided by n minus 2 factorial. So the orbit of this is going to be n choose 2, which is exactly what you would expect, because the orbit of this is going to be all the other inputs, right? all other pairs which are distinct. Okay? So that's, okay. So now, I define a notion that I call the support. For a group, I mean, support has other meanings in the context of permutation group theory, and this may be a bad choice of word, but There was a reason for it. There's some prior history here. But we have a group G. We say a subset of N is a support if any permutation that fixes all of X is in G. Okay? So again, as an example, if G is the stabilizer group of this particular input, then these two numbers, this set of two numbers is a support. Because whenever I fix this, right, any permutation which fixes these two stabilizes this gate. So these two form a support for the stabilizer of this. Okay. So another way of saying this is G contains all permutations which of n without x. I mean, there may be others. So in particular, if it has small support, then its index is big. Right? Again, keep this example in mind, support 2. Groups with small support are big. The converse is false. Take the alternating group. People know what the alternating group means? The alternating group, AN, is simply those permutations in Sn which can be obtained as a composition of an even number of single swaps. I think that's the best way to put it. I started writing it, but this is not so easy to write. Is the composition of an even number of single swaps, ij. Okay? So any permutation of n is obtained as a composition of single swaps. If you can get it as a composition of an even number of swaps, we call it an, and this is a subgroup of Sn. It's the largest proper subgroup in a sense, and it has index exactly 2, right? It's half the permutations in Sn. But this thing doesn't have small support. You can't fix a small number of elements and say all permutations which fix these are in An, right? Because I fix a set X, and among the rest I just do one swap. That's a permutation which fixes everything in X, but is not in An because it's an odd number of swaps. Okay, so unless I fix all except one element, unless I fix n minus 1 elements, right? I don't get something that's contained in An, right? So anything which fixes fewer than n minus 1 elements and allows arbitrary permutations of the others contains things that are not in An. Okay. But if you looked at our translation of FPC to circuits, it's clear that in there, every gate has a stabilizer with small support. Why is this? Because what were the gates in my circuit translation? They were basically subformulas psi together with some valuation for the free variables. And it's clear that any permutation of n which fixes this set, the set of numbers that appear in A bar, fixes this gate, right? So these set of elements, which is bounded by some constant k, forms a support, and so all permutations, n minus k factorial permutations which don't move this gate. So the translation of FPC formulas into circuits gives us gates whose stabilizers have small support. And our main tool for translating circuits to formulas is to show that this is actually necessary in any symmetric circuit. Symmetric polynomial size circuits will always have stabilizer groups for gates which have some constant bound on the size of the support. Why is this? So this is just the statement. If you have polynomial size circuits of size at most n, which is symmetric, then every gate has a support of size at most k. There's some constant k. Okay? And we can actually say something more general than just polynomial size. I'll give you the statement in a little bit, but let's just concentrate on this. We want to say that if it's polynomial size, it has small support. Now, our proof in our original paper for this was rather complicated. I thought rather nice, but I've discovered that there's a much more It's an elegant way to present this by using a result I didn't know from permutation group theory. I discovered this in the book on permutation groups by Dixon and Mortimer, and it gives us a much simpler proof. And this proof basically is the following, right? So I had, actually maybe I've got this on the next slide. I said groups with small support are big, and the converse is false because this alternating group is a counterexample. But it turns out this is the only counterexample, in a sense. This is the fact I discovered reading a textbook on permutation group theory. This is the formal statement of the theorem I found in Dixon and Mortimer's book. It says, if you have a subgroup of Sn, ignore this, this just says if n is sufficiently large and k is small enough. If you have a subgroup of Sn, whose index in Sn is bounded by n choose k, okay? Then you can find a small set, think of this as the support. You can't guarantee that all permutations which fix x are in G, we know that, but you can guarantee that all even permutations which fix x are in G. Okay? So in other words, if the group G is big enough, right, in other words, its index is small enough, then in N, there's a small set X, and G must contain, we can't say all permutations of the rest, but at least all even permutations of the rest must be there. Okay? Right. Take this as a black box. It's given. Okay? Now, how am I going to use this to prove, what I want to prove is that in my circuit, I can always find a small set such that all permutations which fix this are in there. Basically, this alternating group doesn't arise as a stabilizer group. That's what I have to worry about. And this I do by an induction on the structure of the circuit. So we have a circuit, and we know its polynomial size and it's symmetric, so we know that for every gate we can find a set X such that all even permutations which fix X are in this, right? We're given this. So now if we can find any odd permutation that fixes X and also fixes G, then it follows that all permutations that fix X are in G, right? Because it contains the alternating group, and if it contains at least one thing which is not in the alternating group, it has to have everything. The only subgroup of Sn bigger than the alternating group is the whole thing. Okay, so this is what we need to prove. That for any gate G, there is some odd permutation which fixes X pointwise and still fixes G. Okay, so let's see, why is this true? We prove this by induction on the depth of the circuit. So start with input gates. An input gate, we know this to be true. I told you, an input gate is of the form RA. So anything that fixes the elements in the input fixes the gate. By induction, suppose we have a gate such that this is true for all the inputs to G. And now we want to prove that it's true for G as well. Okay? I'm assuming that G computes a symmetric Boolean function. What do I mean by this? Something that's invariant under permutations of its inputs, like and, or, not, majority, threshold. All of these are symmetric, right? They're invariant under permutations of the input. And I assume that this is the circuit is rigid, so it has no non-trivial permutations other than these, which means that if a permutation fixes the set of inputs to G, it also fixes G. Right? You can't have another gate with exactly the same set of inputs and of the same type. That would violate the rigidity of Cn. Okay. So let's say the set of inputs to G, let's call it capital H. And by the induction hypothesis, each of them has a support of size at most k. And let's assume that this is false for G. It's true at all inputs to G and false for G, and we're going to derive a contradiction. Okay. Now pick any pair ij and look at the swap of ij. This is an odd permutation. By hypothesis, this doesn't fix G, so it must move some element of H to outside of H. Right, some element of H to outside of capital H. It follows that the union of supports for the elements of H must include all of this. Okay, because if you leave something out, then this thing, swapping these two will move G, but because it's not in the support of anything in H, it can't move them. Okay. So we can find each of these has small, so each of these supports is small. The union is this whole big set. So we can find lots of things with disjoint support. Okay. Now we have lots of elements of H with disjoint support. Inside these supports we can find individual swaps, ij, which must move that particular H somewhere else while leaving everything else in this set fixed. And we can do this independently. Because these are disjoint supports, we can do this independently. And this gives us, we can find 2 raised to the power n minus k over k, different gates to which G must move based on these different combinations of swaps. And that's a contradiction, right? The orbit of G is now something bigger than polynomial. So that's the proof. The whole conclusion in our original paper is roughly this. I said for polynomial size circuits you get constant size support. More generally, for any size up to something like this, you get supports of something that's order log s divided by log n. In particular, when s is a polynomial, this is a constant. Okay. So now, what have we proved? We've proved that everything in a circuit has, on a polynomial size circuit, has small support. How does this allow us to translate these circuits back into formulas? So we're assuming we have a uniform family of circuits, so there's some polynomial time function that generates these, which means given an ordered set, I can do any polynomial time computation in fixed point logic, so I can write down some formula which interpreted in this will generate the circuit Cn. Okay, it'll kind of define relations on this ordered set which define the circuit Cn. We can also show that these supports that I showed that exist can be computed in polynomial time, all of it in FP, right? We have the circuit, it's on the ordered set, we can compute their supports. Now what we don't have, the structure itself is not ordered, and what we want to do is we want to know whether there is some mapping of n to the elements of the structure, some bijection, such that when you evaluate the circuit with these inputs, it comes out true. But now what we can prove is, for any gate, whether the gate is made true or not under an assignment doesn't depend upon this, what happens to this assignment anywhere else except at the support, right? The things that are in the support is what matters to evaluating this gate, because permuting things outside the support doesn't change anything with respect to this gate. But these supports are a fixed size, so we can express those tuples which assigned to the support make the gate true as a relation of bounded arity in the original structure A. It's a relation, and we can show that it's definable by an induction on the circuit. We can define this relation for every gate. At the output, you produce the value of the circuit. The output, if it's a single output, will have empty support, and it'll be a single Boolean value. So we basically can turn the evaluation of the circuit into an FPC. We're kind of doing this symmetrically in the sense we're doing it simultaneously for all possible permutations of n. The point is that even though there are n factorial different permutations, all that matters at any gate is some polynomial sized piece of this, which is given by what the permutation does to the support. Okay, that's the key idea. So it can be all done. Now, if our circuit has only AND, OR, and NOT gates, you can do all of this in FP, but you needed this on the side, remember, to start with. If we have threshold gates as well, we need FPC, but then we don't need this on the side because in FPC we have numbers anyway, so we can use them instead. So the two theorems I had, do I still have them? No, anyway. The two theorems I had, FP is symmetric circuits on graphs with the order on the side, and FPC is exactly symmetric circuits with threshold gates, both follow from this. Right. it's time. I actually have one more thing I had planned to do, but I'm not going to have time for. What I was going to show you was, so we've now proved the equivalence of symmetric circuits with these relational machines at FPC, and we have a means for proving lower bounds on these. My last bit was going to be just showing you that we can forget about the logic and think of these bijection games directly as a technique for proving circuit lower bounds. You can play bijection games just on using circuits and inputs to the circuits. And roughly, this is the theorem. If you have a symmetric circuit, where every gate has support of size at most k, and you start with structures which are, let's say, 2k equivalent, then the circuit can't distinguish them. And you can prove this directly by constructing a spoiler winning strategy that follows the structure of the circuit. Okay, but I won't do this here. Let me just see. I'm going to skip this proof sketch and just point out this consequence. So what's nice about this is that we can relate. Now we can forget about the uniformity of the circuits and about FPC. Any family of circuits, if we have a class of structures of counting width k, then the family of circuits you need for it has size something at least 2 to the k. 2 to the k? Sorry, that should be n to the k, surely. N to the k, yes, sorry. Okay. Yes. And a little proviso here which falls out of the proof, but I'll stop here. Right. So, just like yesterday, I would happy to first take any questions and try to answer your questions if you have any. Otherwise, if there are no questions, I've got stuff I can fill the gaps with. But anybody? So, what I thought I would try and tell you in this bit is show you the hardness results, hardness meaning bounding the counting width from below, and therefore showing things are not FPC, for various natural problems, right? We've got this one example, the Cipher-Everman graph construction. I mentioned various others, NP-complete problems and some p-time problems too. How do we prove them? Maybe the natural one to start with is solving systems of equations over a 2-element field. Okay, so what does this mean? And let's even consider systems of equations. So by the 2-element field, you understand what I mean, right? This is structure of 2, 0, 1. With addition and multiplication modulo 2, right? So what's the system of equations over this? Let's just assume restrict ourselves, in fact, to simple things, equations with 3 variables per equation. So we have some set of variables, some fixed set of variables. And what does an equation look like? Well, the only possible coefficients are 0 and 1. So any equation is something like this. And on the right-hand side, we can either put 0 or 1, right? 0 or 1. So I want to think of this as a finite relational structure in the following sense. Universe is a set of variables, and I will have a ternary relation EQ0 and a ternary relation EQ1. This is triples of variables which should sum up to 0, and these are triples of variables which should sum up to 1. So 2 ternary relations. And now I want to say, is this satisfiable? Is there an assignment of values 0 and 1 to the variables which makes all the equations true? Okay? And I claim that this property of a system of equations, of being satisfiable, is not definable in FPC. Okay? So I'll give you some idea why this is the case. I'll give you the construction, and then you can try and you can work out the proof by analogy with what we've seen. You start with a graph G. Let's say 3 regular, right? And large tree width. Okay. Such things exist. I mean, you can get an arbitrary large tree width with 3 regular graphs. I'm not going to get into that, but just take it these things exist. Now I'm going to define from this a system of equations. Well, I'm going to define 2 different systems of equations. But maybe before I get, let me start with what I'll call EG. Okay?
Me?
Yeah.
Sorry, but just we should be claiming that this property is not defined within which logic.
In FPC. Okay. So satisfiability for this is not in FPC. I don't know what let's just call this 3F2. Okay. Ternary F2 SAT. Let's just give this a name. It's not in FPC. Okay. So you start with a 3 regular graph, and now put in a variable. First of all, first version, put in a variable for every edge of the graph. For each edge, of the graph, we have a variable xe, right? And for each vertex, an equation. So each vertex V, which has E, F, and G, 3 edges incident on it, we have the equation xe plus xf plus xg is equal to 0. Okay? At the moment, this is clearly a satisfiable system of equations. Why?
Zeros.
Just set every variable to 0. It's satisfied. First modification, do this except at one particular vertex, instead of a 0 I put a 1. Just for one fixed vertex anywhere. Okay? Now the system is unsatisfiable. Why is this? Well, if you take the equations and add them all up, what happens on the left-hand side is every variable appears exactly twice, because there's a variable for every edge, and every edge has 2 endpoints. So it appears in 2 equations. So you add them all up, you get twice the number of variables, so it's going to be 0 modulo 2. You add up all the right-hand sides, it's 0 everywhere except in one place where it's 1, so it's going to be 1. So this is impossible to satisfy. Okay? Okay. But now I'm going to do something a bit different. Instead of one variable per edge, I'm going to have 2. I'll call them xe0 and xe1. Okay? And instead of one equation here, I will have 8 different equations. Plus xf1, sorry, plus xf0 plus xg1 equals 1. And so on. Basically, I take all the 8 possibilities with 2 choices here, 2 choices here, and 2 choices here. And on the right-hand side, I put the sum of those indices modulo 2, right? So I'll also have xe0 plus xf1 plus xg0 equals 1, xe0 plus xf1 plus xg1 equals 0, etc. Right? Okay, this is one system. It is still satisfiable. Why? Well, if I assign to every variable the value of its superscript, it satisfies all the equations. Okay? And now I do what I did before. Choose a particular vertex, and for that vertex in the 8 equations, interchange the 0s and 1s. Okay, I get a different system. So I call these, I started with a graph, I'll call it EG and E tilde G. Okay, so you can see this is very much like, this is the same idea as the Cypher-Emmerman construction. So I've interchanged 0s and 1s. Now I've got an unsatisfiable system. Why is that? By the same argument as before. Just look at the subsystem of the equations where all superscripts are 0. That subsystem is the same as the one I had before. It's already unsatisfiable, so adding more equations is not going to make it satisfiable, right? So once for one particular vertex, I've interchanged 0s and 1s on the right-hand side, I have an unsatisfiable system. And now, you prove these two are CK equivalent. And this argument is exactly what we did. You have a cops and robbers game on the original graph G. It lifts to a winning strategy for robber there, lifts to a winning strategy for duplicator in the bijection game between these two structures. Okay? I'll leave that bit. I think it is more or less, well, it is what we did before. Okay? And I think this example kind of illustrates what the CFI, the Cypher-Emmerman construction, is really about. It's really kind of coding in graph form this notion. And when I was asked the question, why are those xg and x tilde g non-isomorphic, what I really wanted to do was start explaining this. Right, because here it's very clear. There's a satisfiable and an unsatisfiable system, so they are clearly non-isomorphic as structures. Okay, there's a simple property which differentiates them. Okay, so, but let's take some consequences of this. XOR SAT was one I mentioned. This is a very simple variation. What is XOR SAT? XOR SAT is where you are given a Boolean formula, which is a conjunction of clauses, But each clause, instead of being a disjunction of literals, is the XOR of literals. Right? For example. Okay? This is very closely related to this in a sense. Why? Because this can easily be turned into a system of equations. You take such a clause. For this conjunction to be true, each clause has to evaluate to 1. So, but we have negations, but you can always flip the negations and flip the right-hand side. So this just becomes x plus y plus z is 0, right? That's the same as saying x or y, x or z bar is 1. Okay, so each of these turns into an equation. So there's a clear reduction from XOR SAT to this. Of course, that's not really what we want, but there's an obvious reduction in the other direction too. You take every equation, turn it into a clause. For equations which have 1 on the right-hand side, you leave them as it is. For equations that are 0 on the right-hand side, you just put a negation on one of the variables. Doesn't matter which one. On one of the three, negate one of the 3 variables. That gives you a collection of clauses which is satisfiable if and only if this as a system of equations is satisfiable. They really are the same problem. But now here's what, you could formulate this as a relational structure. How do you formulate it as a relational structure? Here's one suggestion. You have a set of elements which are clauses. You have a set of elements which are variables, right? And you have 2 binary relations. This says that this variable appears positively in the clause, and this says this variable appears negated in the clause. Okay? This is a representation of, as a relational structure of an instance of XOR SAT. And now, I think you should be able to prove that this problem, as a class of structures, is reducible to this one by the first order reduction. Okay? It's not too hard, right? The variables here are the variables there, the equations there become clauses. The relations, as I said, are kind of all definable. It's easy to write down the first order definitions. And so from the unsatisfiability of this, we get, the undefinability of that, you get the undefinability of this. Right? Lower bound on the counting width over here gives us a lower bound on the counting width of XOR SAT. Yeah? How about ordinary 3-SAT? Well, there's this. So let's take 3 XOR SAT. You can give a first order reduction from that to 3-SAT. Right? This is also quite easy. Basically, a clause like this can be turned into, just express this in Boolean form using ands and ors. And there's, that translation is easy, and it can all be expressed in first order logic on the structure that I defined, right? It really is an easy exercise. Sorry? You have a question?
No.
You're not sure it's an easy exercise?
No.
Okay. So, how do you express XOR as in CNF? Okay, it is Sorry?
It's so tedious work that it's easier to see that this can be done than doing this way, right? Even if nobody knows the answer.
Sorry?
Nobody knows the answer, I think, right now, but everybody believes that
This can be done. Okay, okay. So maybe, yeah, I'm not sure it's worth going through the details. Okay. I've got a few other examples. So,
what do you know about a body size? There is reduction from 3 size to 3 cells, or?
no. I mean, look. This is an NP-complete problem.
Okay.
This is a polynomial time problem. So you wouldn't expect a reduction in the other direction, right? Because first order reductions are easy. It would be, yes. Yes, but I'm wondering whether we can prove that it's not the case. Can we prove it's false? I mean, for first order reductions, we should be able to prove that 3 XOR sat is simply not NP-complete under first order reductions. But actually, I don't know this.
Is 3 XOR sat P-complete?
Is it P-complete? No, I don't think so. No, it's not. Okay, but yeah. Okay. So actually, maybe this is I was going to do another example, but maybe this is, here's a good opportunity to make a general statement. Consider the following problem. I'll call it circuit sat. Right? So I give you a circuit. I'm not saying anything about symmetry, right? Just I give you a circuit with Boolean inputs over some set of variables x. How do I give it to you as a circuit? Well, I can encode it as a relational structure where my universe is the set of gates, right? I have the, let's call it wire relation, which is a binary relation, which gives me which gate, is an input to another. And I have unary relations for the types of gates, let's say and or not. And I have a unary relation which marks out the set of variables, and maybe I even have some gates which are constant 0 and constant 1. Right? So I have unary relations which tell me which input gates are constant 0 or constant 1, for example. Okay. That's my relation. This is my relational structure. Universe, one binary relation, bunch of unary relations, and it codes a circuit. And the problem is there an assignment of values to the variables, Boolean values, which makes the circuit true, makes the circuit output true, right? So this is clearly an NP-complete problem. It's a at least as hard as ordinary Boolean satisfiability. But now, for this I can prove that it is NP-complete even under first order reductions. No assumption of an order on the underlying universe. So it is NP-complete under first order reductions. And therefore, it has unbounded counting width, for example. Right? Because we know there's at least one problem in NP of unbounded counting width, the CFI construction, or any of these we've been talking about. And first order reductions preserve this property, so this has unbounded counting width, just by its NP-completeness. So why is this NP-complete under first order reductions? So let's see be a class of structures in NP, right? I want to give a reduction from C to this. So because it's in NP, there is a formula phi of existential second order logic that defines it. Okay? And this formula is fixed. So what I'm going to do is, I want to define a map for fixed phi that takes a structure A to a circuit C, let me put it this way, C, which is a circuit, so that this is satisfiable if and only if A satisfies phi. Right? Okay. So how do I do this? Well, essentially, so phi is, there exists, let's say R1 to RR, so some existential quantification over relations, and then some first order formula theta. Now theta is a formula which can use these relations R1 to RR, but also has other relations, let's call it S1 to SS, which are basically of the signature of A. This is a first order formula, and this is fixed. This is independent of the structure A. I can represent it as a circuit, right? So, and this is just A fixed, well, once I fix the size of the structure, I can represent it as a circuit. But let's say, so I'm given A, I have the size of the structure, and from that I can produce a circuit. C, let's call it C theta. What are the inputs to the circuit? Well, they're all atomic facts of the form R A bar, R I, or S J B bar, right? Where A bar and B bar are elements of A, and R I and S J are over here. So this circuit I can produce just from the size of the structure A. Now, I take the structure A, and that tells me for all of these S's, it gives me whether they're true or false. So I replace them by zeros and ones. And for all the R's, they're variables which are unknown. I leave them as variables, input variables. I now have a circuit. If there is some way to make the circuit true, that means there is some way to make these atoms Ri true, so that this whole thing, theta, becomes true in A. But that's just the same as saying there is some value for these relations, so that the whole formula phi becomes true in A. So this circuit is satisfiable if and only if phi is true in A, right? All that remains, and this I'll kind of leave to you, is that we can go from A to this circuit with a first order interpretation, right? Again, it's details are a bit tedious, but I think I'll just tell you it can be done. So we have a problem which is NP-complete under first order reductions. And therefore any hardness results we have, which are preserved under first order reductions, apply to this. I don't know whether 3-sat is NP-complete under first order reductions. It's also an open question whether there is any problem which is p-complete under first order reductions. Okay, this is unknown. So you have one problem which is NP-complete, and then you can it's go through, for example, this compendium of NP-complete problems at the back of Gary and Johnson's book, for instance, and see which reductions can be done as first-order reductions. You can prove, I mean, it's not easy. This is a published result, that Hamiltonian cycle problem is NP-complete under first-order reductions. You can prove that, so 3-sat, as far as I know, is unknown. I think you can prove probably clique and independent set are NP-complete, and that's those reductions. No. I'm not sure. I mean, because the reductions go from 3-sat rather than from this kind of thing. Graph 3 colorability is an interesting one. Graph 3 colorability, I can prove, is not NP-complete under first-order reductions. There are problems in it. Well, circuit sat cannot be reduced in first order with a first-order reduction to 3 colorability. So for graph 3 colorability, the fact that it is not in FPC doesn't follow just by NP-completeness. The first proof that 3 colorability is not doable, let's say in FPC, or it has unbounded counting width, was 3 colorability. Has unbounded counting width. I say the first proof because there are 2 published things. One is through a sequence of reductions which starts with solving systems of equations, a series of first-order reductions. But the first one was sort of a, if you will, first principles proof with a graph construction, which is a bit like inspired by these Seyferier-Immermann graphs. But I'll give you an idea. So you think of the Seyferier-Immermann graph, but instead of starting with this toroidal grid, you start with a grid. Also put these diagonal edges. So we're now in a 6 regular graph, right? Put the toroidal things. It's a 6 regular graph. And this graph, it's easy to see that if the number of vertices, let's say it's k by k. If k is a multiple of 3, this is 3 colorable, otherwise it's not, right? Because it's easy to see from the structure that the colors have to strictly alternate among the 3 colors as you go along any row or column. So if k is a multiple of 3, this is 3 colorable, otherwise it's not. And the 3 coloring is unique up to renaming of colors. Now, the idea is to replace this with a gadget, but now you have a gadget which does the following. Like the Seyferier-Immermann gadget, it's going to, each edge is going to be replaced not by 2, but by 3 edges. Okay? And these 3 are connected in a triangle. And the gadget enforces that in any valid coloring, these central ones all must have the same color, while these ones so let's call this C, C, C. But you have A and B play the same role as in the CFI, that you can swap any even number of them, right? While keeping your automorphisms of the gadget. And there is a valid coloring, 3 coloring, which puts all the A's the same color, but by automorphism, that means there's a valid coloring which colors an even number of A's the same color, but not an odd number, right? And you kind of need to construct the gadget internally to to enforce all these properties. Okay, and you do that, plug it in here, and then the same general machinery applies. You know, the CFI machinery tells you that the graph, you get, you know, with one particular gadget, you switch A and B, and you get two graphs. One of them is 3-colorable, one of them is not, but they are CK equivalent, where K is this thing you started with. Okay, so this is kind of the first proof that 3-colorability has unbounded counting width. I mean, it wasn't phrased in these terms, but there is a proof by means of sequence of reductions also. So yes, so I think I've covered the examples I'd mentioned, right? Yes?
Is it hard to prove that it is not NP-complete under all reductions?
Under first order reductions, right? Well, so the proof that I know is actually a consequence of a strong, what 3-colorability has, or rather its complement, has what's a strong monotonicity property. So if a graph is not 3-colorable, okay, I talked about monotonicity in the context of circuits, right? Rosborough's lower bounds for monotone circuits, and I mentioned that various properties are monotone, like the existence of a perfect matching, adding edges doesn't make it go away. Hamiltonian cycle is monotone in the sense of adding edges doesn't make a Hamiltonian cycle go away. 3-colorability, of course, is not, but its complement is. So if a graph is not 3-colorable, adding edges, it remains not 3-colorable. But it is strongly monotone in the sense that I can add vertices. Once a graph is not 3-colorable, I can add vertices, and it won't make it 3-colorable. I can both add vertices and edges. This is not true of the others. Hamiltonian cycle is not strongly monotone in this sense. Then, you know, a graph with Hamiltonian cycle, I can add vertices and edges and break the property.
Clique is, right?
Sorry?
Clique problem is...
Clique problem is strongly monotone. This is right. Yes. Maybe, okay, maybe we're onto something. Then maybe clique is also not NP-complete for under first order reductions, which would then imply that 3-sat isn't, which I said was unknown. So this is, I look into this. But basically, because of this strong monotonicity, you can show that anything that reduces, so if a class of structures is first order reducible to 3-colorability, then this class of structures is as either I mean, asymptotically, it either includes almost all structures or almost none. It has a sort of 0-1 property. Okay, so in other words, for large enough n, yeah, I can't phrase this better than, so I'm not sure if you know what I mean by asymptotic probabilities, but so this, okay, so define mu n of C, okay, as C intersects, well, I haven't got number of structures in C of size at most n divided by the total number of structures of size at most n. Okay? So this is just the...
1 or 0.
It tends to 1 or 0, exactly. So the things which are reducible to 3-colorability obey a 0-1 law. And therefore, in particular, just having an even number of elements is not reducible to 3-colorability, it turns out. Okay? So, and therefore this can't be NP-complete. The thing's reducible to it. Yeah. So, yes, I should look at clique again. Yes. Okay. Okay, I think I've covered the examples I had, so I'm happy to take any more questions if there are any. So Hamiltonian cycle, I haven't actually got well, I have the paper in which it was proved, but if you're familiar with the proofs of NP-completeness of Hamiltonian cycle generally, they're rather complicated gadgets. And the classic one, textbook one, is not quite first order, but it can be massaged into a first order reduction. It's far from easy to present, and I don't think it's a particularly elegant or instructive one. But yes, so satisfiability, circuit Saturn certainly, and Hamiltonian cycle, we know are NP-complete under first order reductions. There are a few other examples. And for various others, we actually do have counting width lower bounds. Yeah.
Can you say that CFI is in some sense complete? Is there any reasonable way of saying that CFI requires construction for?
Well, I mean, I think the way to show that, the way to say that is the way I did. It has linear counting width, and linear is as bad as it gets, right? But I don't think it's true for any notion of reduction, because you wouldn't expect an NP-complete NP-complete problem to reduce to it by first order reductions. Maybe there's a sort of non-uniform first order reductions one could do, right? So essentially one for each size n, but with bounded width. I'm speculating wildly here, but there's a kind of non-uniform CK reduction notion. Okay. Should we stop here? Okay. Right.